Is this working, or is this adequate?
Yeah, that's on. That's great.
Okay, super. Okay, so in the first week of this program, Jennifer List-Gardner gave a nice introduction to linear mixed models. And one of the things that she said several times during her presentation is that there are several different and equivalent ways of thinking about linear mixed models. So different sets of notation, different subcultures of statisticians and machine learning researchers and so on working on them. But they're equivalent, or at least there's an intersection. So subsets of several models can be cast as equivalent. And sometimes it's useful to think about these models from these different perspectives. Some of my ongoing work is related to that, as I'll get to. So for this presentation, I thought I would try to recap Jennifer's presentation with an introduction to linear mixed models, establish the notation, and kind of use this as a tutorial opportunity. But then show the equivalence to one model in particular, to ridge regression. It's not always clear in discussions that they are the same thing. In a particular kernel ridge regression, they are the same thing again, with the appropriate kernel, as we'll get to. And with that, maybe there are opportunities to kind of cross-fertilize the research, kind of pulling from communities of workers working in one representation of the models or another. All right, so the outline is to go through the model setup, like how I think about linear mixed models and the notation I use. And one particular application is using them for hypothesis tests. So in the genetics context, they can be used for better GWAS as opposed to simple linear regression, for example. Then I'll show how there are equivalent or overlapping model frameworks with the linear mixed model as I present it, and in particular ridge regression. All right, so for this model, we can consider a continuous outcome, a phenotype Y, which is a function of some covariate X. There's an effect size beta that we might want to estimate or test. And there are some unmodeled or environmental factors, epsilon. So in this setting, we could do linear regression, and we'll use that as a starting point for discussion. And linear regression is great when it applies, and the conditions under which it is great are when these errors, the epsilon, are independent. They have the same variance, so they're independent of each other, so the error of the environmental term for each observation is independent to that of the other observations. And they're independent of the covariance. So if those conditions hold, linear regression is awesome. But we might be in a more general setting where that does not hold. So in this notation, we're saying that under the strict conditions where linear regression is nice, epsilon is normally distributed with mean 0. If you have n observations, you can think of the joint distribution of the n errors, residuals, epsilon, as multivariate normal centered at 0 with a diagonal covariance matrix with a certain scale, sigma squared epsilon. In the more general case, we can have a very similar kind of linear model setup, but here we have a general covariance matrix for the epsilons. All right, so if you kind of remember what you do if you're working with a scalar variable and you want to standardize them. So if you're in a scenario where you have a scalar variable, univariate A, which is normally distributed, mean 0, and a variance of 4, if you wanted to adjust that variable to have something with a standard normal distribution, what you would do is divide A by the square root of the variance. So that's how you standardize a univariate thing. All right, so there's an analogy for these multivariate analyses. So if we have a general covariance matrix V, there are several concepts of the square root of a matrix. So if you decompose V into another matrix L and its transpose, such that V equals LL transpose, then L is like a square root of a covariance matrix. And in particular, there are a lot of decompositions that make these matrices relatively easy to work with, so you can invert them and so on. So it's a thing you might want to do for computational reasons anyway. But if we have this framework again, so this linear model y is a function of a covariate x with general noise, epsilon. What we can do is we can do the equivalent of standardizing that univariate variable we had, where we divided by the square root of the variance. Here we multiply by the inverse of one of these square roots of the covariance matrix. But what happens is that on this new scale, where we've multiplied everything on the starting equation, left multiplied by L inverse, the distribution of these twisted residuals, L inverse epsilon, is going to be still mean 0, but now it has a new covariance. And if you do some operations on that, you see that that turns into kind of our nice kind of diagonal again. So by doing this operation, we can convert the general kind of linear model scenario into the one where linear regression is great again. All right, so what are some contexts where we would have a non-diagonal covariance matrix for the epsilons? So one class of scenarios will give rise to block diagonal covariance matrices. So in particular, if you have repeated measurements on a small set of observations, so here you might have two individuals who are measured 3 times each. So you'd expect there to be some correlation between subsequent measurements on a single individual because of, say, unmodeled factors. So with that scenario, you could end up with a block diagonal covariance matrix. In the genetics context, if instead of repeatedly sampling one individual, you sampled families, there's likely to be both genetic and non-genetic similarity that's greater for close relatives than for distant ones. So if you looked at an IBD matrix, and a matrix showing the pairwise identity by descent of pairs of individuals in your data set, say from a pedigree, estimated kinship, close relatives will have high kinship or high IBD, but people who are not close relatives will be essentially 0, and you end up with a kinship or IBD matrix that's similar to a block diagonal matrix. If instead of estimating IBD by something like a pedigree, you just look at a group of supposedly unrelated people, collect lots of genetic information, so say you genotype them on one of the standard arrays, and then calculate their correlation, just person-to-person correlation based on the vectors of genotypes. That is another estimate of genetic similarity, and that will give you a more general matrix, just with lots of small but non-zero things off the diagonal. So a general expression that we might want to use for thinking about these covariance matrices is we might want to say that our general covariance matrix is made up of a structured component. So say that IBD relatedness matrix or a genetic relatedness matrix based on genotypes, and another kind of pure noise component. So in modeling our data, we could model the covariance itself, but we might want to restrict the scope of restrict the space of models we explore, so we're not looking at all possible covariance matrices while we're fitting our data or optimizing various things. We might want to reduce the scope a little bit and look at just weighted combinations of some structure that we think we know because, say, we're basing it on genotypes and a pure noise term. Yeah, so that turns out to be a fruitful way of thinking about these covariance matrices. And going back to the model, we can think, if we're going to use a covariance matrix that's based on shared genotypes, maybe we could model that a little bit more explicitly and see some more connections. So let's say that we are in this scenario where we're going to model our covariance as a weighted combination of a genetic similarity matrix and pure noise. So we could say that we have an expanded version of this linear model we started with. So we have an outcome y, which is a function of a covariate x with some weight beta, and then let's say a whole bunch of genotype z, each with effect sizes b, and then some noise on top of that. In the modeling from this point of departure, a standard thing to do here is to say that the effect sizes associated with the genotypes, they're not unknown fixed constants the way that beta is. Instead, we say that they themselves are random. So you can think of this as a hierarchical model where B's are drawn, when the universe is, the roll of the dice to generate the universe takes place. So B's are drawn. And then phenotypes are a function of the B's that were drawn in the first step and some additional noise and other covariates. And typically the prior or this first step of randomness for the draw of the B's, usually we say that those themselves are multivariate normal as well. Yeah?
You draw the B for every individual at a time, or for every yi, each person draws a different set of B? Or do you draw it once and then every
yeah.
individual will have the same B?
Yeah, so here you would say that there's one, for the system, the B's are drawn once. So they're random in the sense that if you played the universe over, you'd get another set of B's. But they're not random in the sense that in the realized universe or based on a set of data that you actually have, really there is a realized set of B's that you can estimate.
Right.
So it's not random once you actually have data or you've realized an instance of the universe. Yeah.
Yeah, I think it might be equivalent.
Well, if you had different B's for each person, then you couldn't gather.
All of them are going to have normal. Right.
But if each individual has a different draw of B's, then you won't have correlations from person to person based on their shared genotypes. So the strength of this framework is that in the next step you could say, well, even though the B's are multivariate normal and mean zero and so on, because of shared genotypes from person to person and different degrees of shared genotypes across a set of individuals, you'll have different degrees of similarity in this term here, given a realized set of B's. If you had different B's for everybody, then that would kind of break down. Maybe there are richer models that have more steps in the procedure of generating B's, and it's fruitful to pursue those. So there's probably something in what you're saying, but in the standard framework, you draw once. And so in particular, kind of related to that, for a given set of B's and a set of individuals in your data set with genotype Z, you can multiply those two terms, and get the genetic contribution to the phenotype, I'll call G. So this is again multivariate normal, almost everything here is. And we say that the distribution of G now is going to be mean zero again, because B is mean zero, and Z is a constant conditional on the data you have. And the covariance of this term is, you can work it out. It's a function of the covariance of the B's themselves and a product of that genotype matrix with itself. This term, ZZ transpose divided by the number of, in the typical case, SNPs, but I guess maybe in newer applications, epigenetic markers. That comes up a lot, so we'll give it its own name, K. And if this is the distribution of this genetic contribution to the trait, then in that full model that also had a covariate X, we could say that the distribution of the phenotype is going to be centered on the mean model or the covariate model with a variance that's due to the sum of the variance due to the gen X and the variance due to the pure noise. All right, so in the context of people who call these things linear mixed models and the way they're used in genetics, there are a few things that are typically done now. So one is you might want to estimate the proportion of the variance that's due to the two components, the pure noise and the genetics. Sometimes that's interesting by itself. You might want to rescale that, so look at the portion that's due to the genetics divided by the sum of the two. That's typically an estimate of the narrow sense heritability, which is an interesting quantity in its own right. If we have estimates of these variance components, and we know those matrices we started with, we could multiply these things out and get an estimate of this covariance matrix. That may be interesting for some applications. And one in particular that I'll drill down on a little bit is doing better estimation or testing of the fixed effects beta, given estimates of the variance components and then the covariance matrix. And in particular, what you do is, well, by contrast with what you would do if you wanted to estimate that regression coefficient beta in a standard linear regression setting, this is the normal equations, I think. But the thing that you conceptually do when you're solving for beta. You can do better if you know that the observations are not independent. So that's what we're getting at when we say that V is not diagonal. Observations are not independent. There should be some way to leverage that information to do a better estimation of beta, and in fact there is. So this is the way that you would calculate beta given an estimate of that covariance that you would get in a earlier step of a multi-stage kind of analysis. So in the way this would typically be done, you would estimate the variance components, those sigma squareds, then combine those to have an estimate of V, and then get an estimate of beta using that covariance information. And in a not unusual example here, I have some simulated data where there's 50% heritability, so 50% of the variance that's due to these two terms is actually due to the genetics. And I want to test the significance, the non-zero-ness of beta. So here I have a single beta that I'm testing. And if you do not use the information that's in this partitioning of the variance across these two terms here, or the similarity of the genetic contribution from person to person because of similar patterns of genotypes. If you do not use that information, you're using linear regression, you get a reasonable estimate. Here's the truth. Here's an estimate. Certain standard deviation. And in this case, there was enough data to estimate beta well, so there's a quite significant p-value. But still, if you do use this other information, the covariance information, you're in effect explaining away half of the variance that's still in these two terms here. If you ignore this knowledge that you have about ZB, or the genetic contribution, you're just kind of treating that as like more noise. So if you want to boost your signal-to-noise ratio, have a better chance of finding things or showing that they're more significant, conditioned on all the data you have instead of some of it, you would take into account the information you have about this. And when you do that, you get a better estimate of beta, and you get smaller standard errors. You get bigger test statistics and smaller p-values. So things are great. And this is one of the applications where these models are very useful. So that being when, say in the genetic setting, you want to estimate or test your favorite SNP, you think you have a polygenic trait, so you have genetic variation that does contribute to the phenotype that's represented by markers that you have in Z. So using that information, you explain away some of the noise, you improve your signal-to-noise ratio, do better estimation and testing.
In the case of your band that are always inflated, or in one scenario, could you just that are inflated and
In general, linear regression gives unbiased estimates. And under those strict conditions, where you also have the condition that the errors are normally distributed. So if the errors are independent, identically independent of each other, independent of the covariates, normally distributed with the same variance, then linear regression is great. You'll get unbiased estimates, valid p-values. All right, so if any of those conditions break down, as long as the errors are still independent of the covariates, you'll have unbiased estimates from linear regression. But if those other conditions don't hold, the p-values are no longer valid and the standard errors aren't valid. For the linear mixed model and the alternate estimate formula that uses the V information, if you, for some reason, know the true V, then that has a lot of optimality properties again. So you have an unbiased estimate. It's the smallest variance or best power unbiased estimate possible. If you don't actually know the true V, you have an estimate of it, then strictly speaking, all bets are off. You might be biased. You might not even have good power. But in practice, you often have better power and aren't particularly biased. So in practice, it often works great, even though guarantees do not hold unless you, for some reason, have the true covariance model. The linear regression is unbiased under pretty broad conditions, but the p-values and standard errors won't be well calibrated, so those won't be right even though the estimate is unbiased, unless all the conditions hold. And this is kind of what I just said there. So linear regression is great because it's unbiased under pretty broad conditions. Linear mixed models are biased unless for some reason you estimated the covariance model correctly. In practice, they often do well even though you are working with estimates. If you don't have all the assumptions holding, then standard errors are wrong in both cases. And if you do get the covariance model correct, then you have, in some sense, the best possible estimator using the linear mixed model and that estimating form I showed earlier. All right, so now I'm going to look at the same starting model here, and to simplify it a little bit, because they're not relevant to the discussion right now, I'll say that we don't have any fixed effects. We don't have any covariates that we're worrying about here. This might just be an intercept term anyway, but if we center the phenotype so that the mean is 0, we don't even need that. So let's simplify this and say we only have these terms, the genotypes, in a genetic example. And let's say we have n people and m of these genotypes in the matrix. And let's say that our project now is to estimate that set of effect sizes B. All right, so we could try linear regression. The problem there is that we often have many genotypes. So if the number of genotypes equals the number of observations, then we will we'll estimate the phenotype exactly. That kind of tells us that we're not doing anything at all useful, though, because we just have our data there. We have no sense of how accurately we did that. And if m is greater than n, then standard approaches to linear regression won't work at all. Looking at that a little bit more, so here's the linear regression formula again. If you wanted to estimate B using standard linear regression, here's an equation you could do to get your estimate. The problem is that if the number of markers is bigger than the number of observations, then you won't be able to invert this matrix. So it won't be full rank. And you have to do something to work around that problem if you want to stay on this path at all. All right, so one thing you could do, you could justify this different ways. One is just empirically that if you can't invert a matrix, if you add weight to the diagonal, eventually you can invert it. In our case, this is positive semi-definite. So if you add any weight, so lambda is just bigger than 0, you'll be able to invert. Yeah. So that gets around the practical problem with using something like linear regression right here. So maybe we could use a modified estimate of the effect sizes B using this form here, where we just add some weight to make the matrix invertible and stop us from stopping. All right, so this is a common estimator. This is the ridge regression estimate for the effect sizes B. All right, so here we have a way of getting an estimate of B, like even when we have more genotypes in people, say. We can do that with a linear mixed model as well. Some funny notation in linear mixed models, they call estimates of B predictions because they're random, so you're predicting this random thing, even though, as we were kind of discussing earlier, you really have a realized set of those because the universe has been instantiated, but whatever. So the standard approach for estimating B in the context of linear mixed models, which is optimal again if you've estimated the covariance matrix correctly. Optimal in the sense that it's the minimum mean squared error, and it's unbiased. But here, unbiased means that if you play the universe over and over, on average, your estimates will be 0. So it's not unbiased in the sense that in my universe where I have an actual data set, I calculate B. It actually very much is biased. And in particular, with the standard setup, all of the B's are going to be a little bit closer to 0 than an unbiased estimator would put them. Anyway, so with that setup, yeah, we can estimate B in the linear mixed model framework. Remember, then something's not going to cancel over here with the sigma squared E. But if you play around with that, you can see that this is actually equivalent to that. So the kernel ridge regression is equivalent to the linear mixed model if this parameter lambda in the ridge regression setting is sigma squared epsilon over sigma squared G. So they are the same thing, just you talk about the variance components for the linear mixed model or the regularization parameter for the ridge regression. Kind of slightly different, but they get you to the same place. So they're basically the same model, but they're used differently. In linear mixed models, the variance coefficient, the variance components, these two sigmas, the sigma squared G and the sigma squared epsilon, those are estimated by a variation of maximum likelihood for the most part. Whereas in ridge regression and kernel ridge regression, the parameter lambda is estimated by cross-validation. So you partition the data into subsets, estimate like all your parameters, your B's, as I was describing them earlier, and a portion of the data, then predict the outcome, predict the Y's in the left out set, look at how much error you have, and then fiddle around with the lambda until you minimize the prediction errors. So that's how lambda is optimized in the ridge regression setting instead of maximum likelihood using the full data. So it's a bit different. That's a little bit out of place here. Something else about residuals that maybe I'll come back to. Or maybe this is out of order. Might be missing a few. I lost a couple slides. Okay. How much time do I have? Okay. Yeah, anyway, so the slides that I cut out or commented out or something, we're going to say that, okay, so we have these two representations of a model that's essentially the same. Sorry, I'm going to use the board for just a moment. We have two representations of the model that are essentially the same, except that for cultural or whatever reasons, you use cross-validation with the ridge regression and do maximum likelihood or restricted maximum likelihood with linear mixed models. All right, so from the cross-validation perspective, does that give us something useful, maybe that we could borrow and use in genetic applications? All right, so first of all, cross-validation, in principle, that could be a bother, because you have to partition the data into different subsets. So you have a big set of data, partition it into groups, and then say, estimate the parameters of your model using all but one of the groups, make a prediction in the one that you left out, and then look at the residual. So the difference between the actual outcome and the predicted outcome. And then cycle through. So now leave this one out and predict using everything else. You can partition into different sized groups, but like one extreme is to partition every individual out. So you leave one person out at a time. So in principle, then you have to estimate the parameters of your model n times if you have n people. So that might be prohibitive. But it turns out that it's not, because if you're in a setting where your outcome is equal to some matrix times, or your predicted outcome is equal to some matrix times your input, which is the case because for ridge regression, we have this, and all this, if you multiply it together, that's just a matrix, H. So in this setting where you have a linear model in a very general sense, y hat is equal to h times y. Then we can talk about the vector of diagonal elements on h. That'll be useful. So with this setup here, if you just fit the model once, so don't do cross-validation, just use all the data, fit it, and let's say we get estimates of the outcome for each individual. Subtract those from the true value, so we get residuals from each individual. If we take those residuals and divide them by the diagonal element of this H matrix, then that's going to be equal to the residual that we get from this leave one out cross-validated thing. So we fit the model once, and then we do this little thing, which is basically for free, because it's just elementary operations on things. So, so that's kind of neat. So we can do our out-of-sample calculation of residuals. You could square those and look at the mean squared predictive error pretty efficiently in the ridge regression setting. In the linear mixed model setting, yeah?
You do that just once for every lambda, right? You still have to play with each lambda of lambda. So
This is how they choose lambda in the first place. Yeah. So you still have to go through that bother of trying different lambdas and doing a Brent search or whatever, but at least you don't have to do a inner loop optimization.
So you're saying that for a given lambda, you can efficiently compute what would be the
Yeah.
error.
Right.
And now you have to play with the different values of lambda.
Right. Right. Yeah. So that's one thing. So instead of looking at these out-of-sample residuals, you might want to say, okay, you could use the regular setup to make a estimate of the fit value or the predicted value of the phenotype. So in the linear mixed model setting, this would be like calculating a BLUP. All right, so we can do those. And there is there has been a suggestion of a different way of, say, testing your fixed effects. So the first thing that I showed was how you can calculate beta using linear regression or using linear mixed model, generalized least squares. Another idea that has been out there is, so we have our outcome is equal to coefficient times covariate plus the genetic stuff plus noise. Maybe we could estimate this genetic stuff, that's our BLUP. Then maybe just subtract it from the phenotype to get a residual. And then just do, I'll call these like y tilde. And then just do linear regression of y tilde on betas. All right, so that has some appealing properties. So one is that you don't have to do a whole bunch of matrix vector operations, like in the calculating of these effects beta. Also, for some downstream applications, you might be, so instead of subtracting this thing from the phenotype, you might just want to keep it as a covariate. So that also might be kind of neat, because now you just have a covariate. You don't have a weird matrices. You have a covariate, and you might be able to throw that into your pipeline of dealing with covariates in interesting ways. The problem is that when people do this, and there were a few papers describing the method, and then a lot of applied papers like in animal science using it, and then a paper saying, well, the results are biased and the power is not great, but here's a hack that sort of fixes it. The problem is that here you're calculating a BLUP, and then you subtract it from the outcome. All right, this is calculated like in sample, so it overfits the data a little bit. So you make an estimate of this term in your sample. the epsilon that we wrote here, that's basically stuff that you haven't modeled. So when you overfit your data a little bit, your estimates of the BLEPs are going to be a little bit correlated with everything else that wasn't modeled. And if that stuff that you haven't modeled is actually what you want to turn around and learn about in the next step of your analysis, then you're subtracting some of it out when you do this, or you're conditioning on something that contains it. If you use this as a covariate. So, all right, so if the problem is overfitting, why don't you just do efficient cross-validation using that same trick that's common in ridge regression? And it turns out you can, is if, so if G is equal to ZB, then we can fit the linear mixed model once and get our BLEPs. And we get our BLEPs from the BLEP formula, which is that. All of this stuff is a matrix. So we're in the same setup as that ridge regression. We have our estimate, our BLEPs, that we calculated the standard way. Now we can do G minus using this, so like a little bit of algebra applied to the formula for getting those out-of-sample residuals. You can get out-of-sample BLEPs as well, or I've been calling them cross-validated BLEPs. So you can kind of do this for free after you've calculated BLEPs the standard way. If you do this, then calculating these residuals or using these cross-validated BLEPs as covariates works brilliantly. The power is better. That you get unbiased estimates of your B, and these cross-validated BLEPs are almost uncorrelated with the residual, with the error in the model. So if you do a simulation where you can actually check, the correlation is pretty much broken. So if you're doing a sequential analysis where you kind of calculate things in step 1 and then do something with them in step 2, these are interesting quantities to kind of calculate and then do stuff with in subsequent analyses. And I have a number of things kind of in progress, kind of showing games that you can play with these cross-validated BLEPs, in addition to doing this residual analysis or like covariate type analysis to estimate fixed effects. They're useful for other things, namely if you calculate them for several different traits, then you can look at the correlation of them. That's an estimate of the genetic correlation. If you calculate them for several different traits, then you can use them as covariates in the same model. And that's a rough and ready way to kind of do a multivariate analysis instead of doing much more complicated linear mixed models with multiple phenotypes. You can calculate those BLEPs one phenotype at a time and then play with them. So that was something that I was able to put together because I'm playing with these linear mixed models. I'm sorry. I don't know if I have any slides left. I was playing with linear mixed models, and I was thinking about them in terms of ridge regression. So I was able to kind of put this trick together here. But because linear mixed models have other interpretations, I think I'll just kind of end shortly here. They have other interpretations, and those different interpretations of the same kind of fundamental model suggest different extensions. So the linear mixed model, the way it's usually formulated, you have your V is a weighted sum of a couple matrices. So in the standard case, V is equal to sigma squared G times K, a genetic relatedness matrix, plus sigma squared E times a diagonal. But you could have more terms in there, some more variance components. And you may want to, because you may have genetic information and also repeated measurements on the same individuals. And also you might have some proxy information about environmental exposures. And also you might have cell type information because you're doing methylation data analysis or something. So thinking about this model in terms of variance components suggests one way to expand them, which is bring in more variance components. Thinking about it in terms of ridge regression, as ridge regression, the kind of key innovation over doing linear regression is you had that lambda times identity, that went into that matrix we had to invert. So that's an example of regularization. So there's an awful lot of current research on different types of regularization, which often includes discussions of ridge regression in comparison to other methods. And in very high dimensions, ridge regression actually is competitive in a lot of scenarios, so it hasn't been necessarily surpassed by the other things. But thinking about these models as regularized regression will key you into that body of literature. If you don't have enough references for your favorite models in the journals you currently read, you can look up that. Because the linear mixed model actually corresponds to kernel ridge regression, where we use the genetic information in the form of a person-by-person matrix. In the genetics context, those matrices are the correlation. It's a matrix where cell ij is the correlation of person I, person j based on their genotypes. All right. So in the broad sense, you can work with other kernel matrices, where a kernel matrix is something where you take two vectors of input for two people, and you multiply them to get a scalar output. And there's been a lot of fruitful research playing with different kernels, including some in the genetics setting. I think there's a recent paper by Sharon who was here kind of earlier in the program. A particular example of a kernel matrix is, instead of using a genetic similarity matrix, just using a distance matrix. So you might have geographic information about where you collected your samples, and that might be relevant. That's actually a very common model called Kriging, and that has been combined with genetic analyses. So like when you have spatial sampling information about where you recruited subjects for a study. So that could be combined using a particular kernel and also using a multiple variance component approach. And the betas, or excuse me, the Bs, the random effects, the BLUPs, here we were saying that those came from a multivariate normal distribution, mean zero. You could say that that's a prior for the Bs. And then once you start thinking about this in terms of hierarchical models or Bayesian models, maybe you could try other priors. So there's a lot of, there has been a lot of work, and some of the stuff I've been playing with is using mixture priors. So with some probability P, a B, a BLUP, is exactly zero. Otherwise, it comes from a normal distribution. Or maybe it comes from two normal distributions, one with a very big variance, one with a very small variance. And that will capture the idea that probably a lot of genetic variants don't contribute to your trait. So it's a way of getting sparsity or squashing the contribution of most of the stuff there, because it's probably not useful. And there are other priors to play with, a lot of things there. So these are all different representations of the same fundamental model, but because people look at them slightly differently, that suggests different ways to extend them. And that might be kind of useful. I'm sorry I'm missing a few slides here, but I think the punchline is that ridge regression equals kernel ridge regression equals linear mixed models equals hierarchical Bayesian linear models. And if you like these methods, it's worth reading the abstract of the paper whenever you see any of those words.